Okay, so let's start with the trap ion. This is based on two articles. One is this book, Atomic Physics by Foote. This is a very famous book for atomic physicists. If you have chance, you can borrow from the library or read it. It also discuss the last two chapters discuss the quantum computer. But all the basics are there. And also based on this paper, Equilibrium ion trap quantum computing, right? It might not be the state of the art nowadays, but all we need is just to learn some basics. So I will continue to use this paper. So let's go back to ask ourselves again, what is required, what are required to make an architecture suitable for quantum computer? We have learned about spin qubit. We follow the DiVincenzo's criteria. The spin qubit has two levels, spin up, spin down, a very well-defined two-level system. We were able to initialize the qubit in spin qubit. All we need to do is just that it thermalize, or we actually, when we talk about the silicon spin qubit, we try to borrow some higher level to excite it and then to let it decay, right? Through spin selection or through the so-called spin to charge conversion, if you will. There are many different methods, right? So we can initialize it. Regarding the decoherence style, we did not discuss much, but we definitely say, hey, we need to have a very pure environment. So we purify the silicon, right, to have more silicon 28, right? If I correct, suddenly forgot, right? So that, but then in the natural resources, we have more silicon 29, right, which have spin half nuclear spin that is going to cause decoherence to the silicon spin qubit, electron spin qubit, right? We talk about universal set of gates. We can have a single qubit gate, right? How about, do you remember what else do we need in order to build a universal set of quantum gates besides arbitrary a few of the single qubit gate, Hadamard gates, right? T gates, phase gates, right? What do we need? What else do we need? Can I say again? C-naught gate, which means it's an entanglement gate, right? So for the spin qubit, we actually don't have the C-naught as the native gate, right? Do you remember what we use? Maybe forgot. It's the control phase shift gate, right? The C phase gate. But we can always convert it to a C-naught gate by combining with many 1-qubit gates, right? And we can do the specific measurement. If you remember, how do we do the measurement in spin qubit? We use spin to charge conversion, right? If it is a certain spin, it will be able to tunnel, and then it will change the conductivity of the single electron transistor, or what else? The quantum dot point contact transistor. Make sense? Do you recall this? Okay, now your turn. Tell me, how about it? How about this can be a hint, right? We can do this in the exam. How about for superconducting qubit? What did we do in order to get a two-level system? You probably need to recall, keep saying, and then correcting. What did we do? How do we build a two-level system in superconducting qubit? What's the latest one that we just learned? Huh? Transmon, yes. So we use a Josephson junction and a capacitance to form something like the LC tank. Then we have many levels, equally spacing, but however, because we use Josephson junction, it is non-linear. As a result, we have anharmonicity. Remember? So it is not as clean as a spin qubit, but we form a level like this. This is ground level. This might be the first exciter level, and this is the second exciter level. The spacing between the E10 and E21 are different. So basically, if we do it right, we kind of confine it as a two-level system, right? This is, let me call it transmon. Correct? But just treat this as a review. I won't have time to have another review. We only have 2 more classes. Okay? Okay, fine. So we have a two-level system playing with this 0, 1. If remember, ask yourself what is the meaning of 0 and 1? That's the fault state, right? It is not the excess number of Cooper pair. It's the fault state, right? Okay, then we ask whether we can initialize the qubit for transmon. We did not really discuss much, but if all of them are just similar, we can use thermal reset. We just wait for a long time, then the excited state will go to the ground state. Or we can use active reset, that we measure it. If it is at 1, we apply a pi pulse, a rapid oscillation, to bring it to 0 state. And then if it is 0, then we don't do anything. That will help us to reset to initialize the qubit. How about the decoherence time, right? We did not say how to do it, but we touch a very important topic about how do we design it so we have a long decoherence time. What's so special about transmon compared to charged qubit? Do you still remember this diagram? This is NG, right? And then for transmon, it is something like this for different level. What does this mean? What is NG? No one have studied review yet, right? There's the offset charge due to the coupling from the gate, right? So it is less charge sensitive for transmon because NG can be induced by environmental noise. So here, if even we change the NG, the frequency, the qubit frequency does not change much. So we say it is insensitive to charge noise. Make sense? So go back to review this slide, listen again what I said, write down a table, compare the 3 different technology. I have an idea what to have in the final now, at least for one question. Okay, that's a hint. Review again, right? How are these related to each other? Regarding universal set of quantum gates, no problem. We already derived the Hamiltonian. We quantized the circuits, right? I showed that we can do 1 qubit gate by applying a sinusoidal signal. But how about for 2 qubit? We need an entanglement gate. Do you still remember? Probably you don't because I rushed a little bit. What was the native gate for a transmon qubit? For an entanglement gate for 2 qubits. Yeah, that one I did not go into detail, really rush, right? It's the I swap gate. Okay, so listen to this portion again. I swap gate, right? I really did not go into detail, so it's not your problem. But using I swap gate, 2 I swap gate, and many 1 single qubit gate, I will be able to construct a C0 gate. So from there, I also build a universal set of quantum gates. And regarding measurement, this is very important. We spend a lot of time to discuss the measurement of superconducting qubit. How do we measure it? What are the keywords? Cross-cut, yes. And how? If you can say the keyword, what does it mean? Coupling of what? Resonator and qubit. Okay, very good. So we couple resonator to a qubit in order to do the measurement through the cross-cut. So now can someone give the final answer? How do you measure 0 and 1? In the architecture I show you. You send a pulse to the So you send a pulse to the resonator and then measure the transmitter signal, right? And the transmitter signal can give you, only has a big response at the resonant frequency, correct? Yeah, so you're right. And then because of the coupling, the cross current, the state 1 and state 0 of a QB is going to change the resonant frequency of your resonator, right? For example, if the QB frequency is lower than the resonance frequency, state 0 will give you a larger resonant frequency. State 1 will give you a smaller one. Then by measuring the change of the phase of the signal, then you know whether your QB is at 0 and 1, right? So there are lots of stuff that we have learned. I know it's going to be very confusing, and it's impossible for you to be able to comprehend within this semester and provided the time you have put into this class. But that doesn't matter because luckily it is already AI era. The point is that you need to keep thinking and have independent thinking, okay? Yeah, I want to warn everyone. I found an issue with some student. I have a student who tried to do, recently I asked you to do research with me. I gave him a simulation, TCAT simulation deck. I said, go back and understand what it is because I want him to reproduce using another things. And that student just submitted to ChatGPT and ChatGPT summarized to him, which is good. Looks like he knows what I sent him is about, but that is not the end goal. The goal is for them to really understand what does that input that or that program is about, right? And if you don't, when you're studying, when you ask ChatGPT to help you, you need to make sure that you get the knowledge you want. Do not think that you really understand if you don't know what you're looking for. That is going to affect your interview or your job, okay? ChatGPT, use it as some assistance to you only at this moment, right? But it's very useful. You definitely should learn how to use it for productivity, but be very careful. Fine, so I spent so much time, let's treat it as a review, okay? Now, then we want to talk about the trap ion. So I'm going to show you these 5 criteria again for trap ion. So the first thing is 2-level system, right? Spin QB, we use electron to carry the signal, the information, the spin of the electron. Transmon QB, we use the Josephson junction and capacitor to carry the fault states, or in charge QB is the excess Cooper pair, right? Now then, how about for a trap ion? First of all, not every ion is suitable to use for trap ion quantum computer, right? So one of the commonly used one, I'm not sure if this is the state of the art, but let's just learn the basics, is the ytterbium. It should be YB, right? And this is 70 and 171. 70 means it has 70 protons. 171 means it has 171 electron and neutron, right? So one is the mass number, one is the atomic number. So 171 is an odd number. This is special because we need to have a spin of the nucleus. So neutron and proton have half spin. Just like electron, if you have even spin, even number, they will cancel out. Just like the Cooper pair, right? You cancel out the spin. So we do need to have an odd number. So first of all, this is just the atom. This is not the carrier yet, but we use this atom. And its electronic configuration is this. I bet many of us have forgot what it is. Not very important again, but if you want to go to interview with a trap ion quantum computing company, you better review it, right? But anyway, here you say that it has the complete shell as Xeon, okay? And on top of it, on the 6th orbital, it has S2. You feel the first suborbital. So let's review a little bit, right? If you remember the quantum number n, first orbital is 0, 1, 2, 3, right? Keep going, right? And then you have the azimuthal quantum number, which is it L? L, right? It's also 0, but we also call 1, 2, 3, but we call it SPDF. Keep going. So, right? So when you say S, it means this is the first suborbital. Some of you forgot. So you have a principal quantum number, the first orbital, first shell, you can fill 2 electrons. Second shell, you can fill 2 to the power 2 times n to the power 2, right? Electron. First shell, 2 times n power 3. So this is this n, right? Does it start with 1 or 0? Maybe I'm wrong. It starts with 1, right? Start from 1. Yeah, that's why 2n squared, right? So hydrogen, you only fill the first 2 cells. Helium, you have just 2 of this, right? But then within each of them, your L will go from, right, L in each main orbital, the L go from 0 to n minus 1, right? So for example, for the first shell, you only can have 0. You only have S, right? But anyway, so if you still forgot about it, it's fine. You need to study if you interview, right? I'm not going to test this. I just want to remind you about this because some of them will help us to explain something later. But the point is that this is the electron configuration. It has 1, 2, 3, 4, 5, 6. If you 6 major orbital. For those before 4, right, it is completely filled. And then you also have this subshell field. 5 also filled. Okay, is that okay? Now, so this is just the atom. I just introduced you this atom. But the carrier is what? For the trapped ion here, the carrier is actually ytterbium plus. Means that it's going to lose 1 electron. So if it lose 1 electron, the ion, right, because it's a trapped ion, so it is an ion as the carrier, is 4F14 6s, right? Because I lose 1 electron from the 6s shell. So this is, it is big. If you treat this, you ignore this, this is just like the hydrogen atom, right? I have 1 electron on the S shell. Okay, but I think this, I actually forgot. This F shell, 4F16 shell actually may be surrounded, is protecting this one a little bit. That's the first thing, right? I hope you can recall. If not, the only final thing you need to know is, yeah, ytterbium ion has 1 electron in 6s and ionized, okay? Yeah. Thank you. I missed the one. Thank you. Okay, that's it, right? That's all you need to know. Now then I want to introduce another concept, right? It's called the fine structure. So if you remember, you learned from chemistry, how did people discover the energy level of hydrogen or other atoms? What they do is actually they shine the light through the gas, and then they find that some got absorbed, right? And then you have this line in the projection, right? Those wavelengths got absorbed will become dark, right? And then, of course, then they try to explain, they say, okay, because the discrete system, you go from 0 to 1, you absorb that amount of energy. That's why you lose this line, this color, right? They got absorbed. Or through emission, right? I don't know the details. But then if they try to amplify it and do it at very low temperature to avoid the noise, they find that this cannot explain the color, because they find that for Fe9, they actually, for some lines, they further split into some small distinction. That it means there are some level within the theory here, and that is due to and this is called a fine structure. We don't need to think too much, but the main point is this: why we further have energy difference, and that is due to this. My electron is rotating, right, classically. He has angular momentum. It's rotating, right? Then, what happened? A charge, a moving charge, will cause what? Just like the current, looping current, what will it produce? Thank you. It will produce magnetic field, right? This is a very hand-waving discussion, but it is correct if you even do the quantum treatment. Good. So the electron move, they are moving, they produce magnetic field. But do not forget, electron, the same electron, let me call the same electron, also has spin magnetic moment. This one we are very familiar with this when we discuss the spin qubit. Right? Because it has spin, so it has magnetic moment, right? So this is B and this is mu. Do you agree? Okay, so it is moving, it produces magnetic field, but itself also have a spin. Then a spin inside a magnetic field, what will happen? Then of course you create an Hamiltonian equal to negative mu dot B. Right? So you just, yeah. Interact with its own magnetic field, yes. Yeah. A very hand-waving discussion, right? This will just create some change in energy. So if you spin up and spin down, then you're going to have your Siemens splitting, right? There's a term, they call it internal Siemens splitting. Just like what we learned in the spin qubit, okay? And for those who have learned solid state physics, you try to calculate the band structure. You probably are very familiar with this. This is what we call spin, right? Which is the S orbit, right? Because you're rotating the momentum, right? Angular momentum, which is due to L coupling, right? Or we call it LS coupling. But anyway, what it means is that electron spin moment, magnetic moment, interact with the magnetic field equator, and as a result, it will cause a splitting if you are spin up and spin down, right? Because your spin doesn't affect the magnetic field; it's the charge and rotating direction. But spin up, spin down is going to give you a different effect. Okay, so this will cause the fine structure. That's the first thing. Is this okay? Now, this is actually a lot of stuff. So if you feel too much, that is fine, but I hope that you know how to find information. First of all, you know that you need to understand that they have the electronic configuration. What exactly it is, maybe you can look up when you need it. Second is that it is an ionized atom. So it's ion, right? Plus charge. And then the third thing is we have this fine structure. This fine structure is very important, you will see later. So let me show you this one. This is the fine structure. Okay. This one are the fine structure we mentioned earlier. right? They all belongs to 6s orbit, right? They all belong to this orbit. But I have two levels due to the spin orbit coupling. Okay? But here I want to introduce another symbol called term symbol. Right? This one will be useful in the future if you try to read the literature. Right? So let me remove this. So what is the meaning of 1p1 and 1s1? Right? So first of all, electron is rotating. It has angular momentum. So it has the orbital angular momentum. So this one, I assume you have learned some quantum mechanics. If you forgot, you just take it for granted, right? I probably won't test this. L, so depends on the orbits that you have, right? It can be S, P, D, F, etc. Like this. However, it's not exactly the same as this SPDF because now the system is more complicated, but it resembles this. Okay, you just take it for granted. It's SPDF. Second, of course, I have the spin angular momentum, right? Or spin quantum number. Let me just call it spin angular momentum. This is not exactly the momentum. This is just the quantum number, but just call it momentum, S. So what are the possible value? It can have many different values because now we are not, it's a more complicated system, right? And then if you have angular momentum, you also have spin angular momentum. Then of course you have total angular momentum. And we call it J. So this is what you will see in the literature, right? Now, for this system, we also need to make an assumption. It's not that simple in quantum mechanics. We assume it is LS coupling, which means J, S, L are good quantum numbers. Now, what does it mean? If you think about transmon qubit, maybe it's easier to think about that. Remember in transmon qubit, I say that the basis state is capital N equal to 0, capital N equal to 1, 2, 3, 4, 5, the fourth state. But they are actually a linear superposition of smaller n, which is the excess Cooper pair. Right? You can have negative 100, negative 99, all the way to 0 to 1, 2, 3, 4 to 100. Excess Cooper pair, smaller n, right? So in that case, the fourth state, capital N, is a good quantum number because it really it does define the state of that system, right? You cannot use a simple small n to describe that quantum state. Or another example, you can just talk about position and momentum. In quantum mechanics, as we said, if I know exactly what the momentum of a wave, then what is the position of that wave? You cannot determine. Yeah, exactly, right? Because the momentum, if the momentum is precise, you actually have a sinusoidal wave extended from negative infinity to positive infinity in order to say that it is precisely that much of momentum. Then you lose all the information of the location, right? And that momentum in that particular case is a good quantum number to describe that system, right? Whether the momentum 1, momentum 2. You don't want to use position because position will be a superposition, right? So this is just say that this is in a certain situation, LS coupling, not all the atom can be described by this coupling correctly. And actually, I forgot, I think it's heavy atom will be better. I forgot when, right? Only heavy atom. But I can be wrong. But anyway, you just take this for granted, they are good quantum numbers. So, which means that to describe this complicated system, I just need to say what is J, S, and L. The total angular momentum, the spin angular momentum, and the orbit angular momentum. Okay? So that is the first thing. So if this is the case, then J will take this value. It will take L minus S, L minus S plus 1, all the way to L plus S, which is understandable. If I have angular momentum, which is L, and I have spin angular momentum, which is S, isn't the maximum is they are in parallel, then it's L plus S. And the worst case is anti-parallel, which is L minus S. Right? I'm not talking about best or worst, but when L and S are parallel, then the maximum total momentum is the addition of them, right? Right? If they're anti-parallel, the minimum one is the difference of them, right? So the J will only take this value. Right? For those who have taken quantum mechanics regarding angular momentum, you should be very familiar with this addition of angular momentum, particularly when you have two bodies, right? But for those who have not, this is not the purpose of the class. I just want to show you this. Maybe you are not going to use anyway in the future, right? But this is understandable, right? The total must be between the maximum, the sum, and the difference. And the only thing that is quantum mechanics is that they are discretized. If it's classical, you probably have L minus S plus 0.1 plus 0.2 plus 0.0001, right? It's continuous. But in quantum mechanics, they're discretized, right? Okay, so then we will write the state of the system as 2s plus 1 L J. We'll write it in this way. Okay? So what does it mean? The superscript is 2 times the spin plus 1. And this L is the angular momentum state, and J is the total angular momentum. Right? So let me give you an example. For example, let's look at the 2s1/2 state. If someone gives you, okay, the state is 2s1/2, what does it mean? Then what is S? This is very confusing. What is the spin value? What is the spin? What is the spin spin angular momentum? 2, say again. 2 equal to 2s plus 1, right? So what should be S? 1/2. Very good. Right? Then what is L? What is the angular momentum? Right? This is confusing. Angular momentum equal to capital S. Because that is the way we write it. Instead of writing number, we write SPDF. Right? So yeah, this is very confusing. It is 0. Means it has no angular momentum. Because I write it as S. S is just the label. Here, S. So it is 0 in value. Then how about J? What is J here? Thank you. 1/2. And then think about, does that make sense? Yes. This time J is 1/2. It is the maximum of this system of J is actually 1/2 plus 0, which is 1/2. The minimum is also 1/2 minus 0, which is also 1/2. You only can have one J value for this system. Okay? So I think I confused many of you. Try to understand, if not, fine. The full exercise is that you just agree with me. After this fine structure, we are going to split it into more level. And we are going to label it with this term symbol. If you're okay to accept it, accept it. If not, you can try to understand what it means. Okay, because when you read the paper, it will show you a family of all these levels and how the electron transits from one state to another. Okay, and that's the only thing the reason I teach here. So the first 2 pages is confusing. Don't worry too much, but it's useful to help you get started. Now, then I want to say another thing called hyperfine structure, not just fine structure. So what is fine structure? Fine structure, again, is the electron spin interact with its orbital angular momentum generated at magnetic field, right? Or you can think of spin-orbit interaction. So I'm running, and at the same time, because I'm spinning, I'm just causing myself have different energy when I'm spinning left and right. But there's another hyperfine structure. So the scientists further amplify the spectrum and find that, oh, it further split. So this is the fine structure. This is the fine structure. Right? And then here we have the hyperfine structure. It splits even further. We thought that it's done. Actually, we still can distinguish another 2 levels within the fine structure. So what are they? So hyperfine structure is very important. Now is the interaction of the nuclear spin. Let's say the proton, the nucleus as a whole, right? The nuclear spin with the magnetic field by the electron, which is common sense, right? If electron spin can interact with its own magnetic field, then the nucleus will also interact with electron's magnetic field. Of course, in the treatment, usually people will just use the electron as stationary. They will go to the rotating frame of the electron. Then it becomes the nucleus is surrounding the electron. And actually, it's the electron fueling the magnetic field generated by the nucleus in that sense. Right? But it's the same, right? You will need to go to relativity, etc. But anyway, this caused the hyperfine structure. And just now we talked about, maybe I should say this, right? LS coupling is like J equal to L plus S. Here we have further J plus I equal to F. Now this, maybe I should start. J, of course, is the total angular momentum of electron, both spin angular momentum and the orbital angular momentum. But I is the angular momentum or nucleus spin angular momentum. Okay, so now I just add the nucleus into the picture, and this is the total of the atom or ion. Okay, now it's the whole thing, not just the electron itself. Okay, so you have this F. Is the logic clear? Don't care about the math, right? We start with electron spin angular momentum plus its orbital angular momentum. We get the total momentum of angular momentum of the electron, which is J. Now you add the nucleus spin angular momentum. That is the total angular momentum of the whole atom of all ion. Right? This is just logic. No worry about the math. And that's why you further split into F equal to 0, F equal to 1, F equal to 0, F equal to 1. So these two are the fine structure, but within the fine structure, the further split into two levels. So I say so much, right? For what? It's for this final conclusion. We are going to use the hyperfine structure of this 2s half state as the qubit state. Right? So then here explain a lot of stuff. Why we need Ytterbium-171? Can we use other isotope that has even speed? No, because we do need to have finite nuclear spin. So it need to be an odd number. Without this, you won't be able to split into two states because there's no interaction, right? So that is why we spend so much time. And that's why I say at the end of this class, if you forget everything, that is fine. Only thing is that you need to appreciate that this splitting, although we keep saying hyperfine, but that is exactly the frequency we want. The energy here equal to h bar omega, where F is about 14.7 gigahertz. That is the range we can handle. For here, it's about 300 terahertz. That is what we cannot handle easily from electrical engineering point of view, right? We can easily generate 100 gigahertz or whatever electrical signal or electrical signal. How do we do this? I mean, just for the equipment we have, this is the one that we can handle easily. Of course, for laser pulse, we can do terahertz. That's not a problem, right? But the point is now, I hope that you understand, we have two well-defined systems. You see it is well-defined because this is hyperfine. The next level is fine structure. This is like in hundreds of terahertz, right? So I can confine my system here. But you should understand this is not the energy of just an electron. It's a combination of the nuclear speed, right? The whole thing. You cannot isolate that. It's just the whole system that giving you the two states. Is that okay? Okay, so we are done with the first criteria, right? We have a two subspace system. So put in your table, right? So let's say again, 171, because it's odd, so I have half nuclear speed that is required for the hyperfine structure, plus white iron, because we want to trap it. I'm going to show you later. And this one is chosen because it has a reasonable ionization energy. And I forgot to say that this is the atom. In order to make a quantum computer out of it, we need to ionize it, right? To make it into the ytterbium plus. So we apply two laser pulse to go through this state, once to here, another to vacuum. The reason is that this can filter out different isotopes. This can make it very pure, right? So I'm not very familiar with this, but you can take a look at the paper if you're interested. So they do this for some reasons, because you have other isotopes, okay? So we have two levels. Now, how do we hold the ion? I now have a positive ion. What it really does is that you can imagine, okay, put it under an electric field, right? So how can you hold an ion? Maybe you will think, let me just have a positive charge here and positive charge here. Then isn't that along this line, it will just stay here, right? Because this is positive, this is positive. But the problem is that it's just like this saddle landscape. Yeah, in this direction, this is the minimum. But in the lateral direction, it is the maximum. Right? Just like you ride a horse, the saddle. You may say, can I put a positive here and a positive here? But theoretically, actually, it is proved that if you do that, this point won't be the minimum. You will not be able to use electrostatic to construct a minimum in the space. This is impossible. right? So you can refer to Foot's book. He has a proof on that. You just take a look, but you just that you cannot, right? In reality, in 3D space, yeah, you can have a lake or a well, then you have the middle point is the minimum energy, but you cannot construct such a minimum energy in the 3D space using electrostatic force. Okay, just the equation does not work. So what we can do is that we use a concept like this. This is mechanical. This is not trapped iron. If I put a ball here, how can you prevent it from falling down laterally? You actually can rotate it. Because when you try to fall down, if you rotate at the right frequency, fall down a little bit, maybe you have this one blocking it. Then you try to fall down in the other direction, but it's rotating, then you are blocking it again. Do you see what I mean? It's just like I have a paper, right? Not paper, just a flat. The table is flat, right? A book, which is flat. I put a ball on it. You can not hold it, right? The ball is going to roll down, right? Because you cannot make it absolutely flat. But what will you do? You will just keep wiggling, right? When you fall to that direction, you try to tilt it the other direction. If you do it right, then you will never fall to the ground. So same here. If you rotate this, you will be able to keep the ball at a point in the space. But you know that it won't be at a point. It will going to wobble a little bit. Same here. This is the idea. So here first, I don't know if you can see, this is the cross section. We have 4 electrodes. And then middle is referring to these 2, right? So you can see that in this lateral direction, right, I have actually an array of iron. They are all positive charges. Of course, they will try to repel each other, right? Then you form a lattice, equally spacing. They will try to leave each other. However, I put positive charge at the end, so I squeeze them, right? So laterally, they are confined. But then they will try to fall away lateral in this vertical direction or into the screen, right? So what do? You will have 2 pairs of electrodes, right? One pair, maybe this is plus, and then this is minus. Then, of course, based on the theory here, when this is plus, it's not going to go up, but it's going to go into the screen, means in this direction laterally. Make sense? If I have the positive ion here, and when this is plus, and this is plus, isn't that it will be squeezed laterally, right? But I apply an AC signal so that later this will become minus and this will become plus. Then when you try to go into the screen, it happened that I changed it to negative, and then this one become plus. This is wrong. Then it won't go laterally. It will try to go up again. But before it can go up, the AC switch to plus already. Then you will squeeze it back. Make sense? Again, it's just like I have this rigid surface. I put my pen here. It's flowing. I just keep going back and forth to keep it in place. But this is a 3D action. Okay? Like the miniature what? Oh yeah, this one looks like that, yes. But here you try to confine the charge. So on the top, maybe have a better view. So you see this is plus, right? You have iron here, what happened? It will go laterally, right? But before, let's say you start moving a little bit, and we just switch the electric field to negative and plus again. Then it won't go lateral, you will try to go up, right? But then I switch it back to positive, then I push it back again, right? So if I do it right, you will just have a very minor motion around this region. Then I can confine it in 3D space. It's floating in the vacuum. Okay? So we will not go into the math, but I just want to show you the results. You can refer to the book. This trap is called Paul trap. It traps the ion. Remember, these are the ion, positive ion. They trap in space. They are really floating in space, right? The potential, right, phi, follow this relationship. Phi 0 plus V0 divided by 2R0 squared cosine omega t x squared minus y squared. And here is x, and here x and y. So it's just saying that how the potential changes, right? But this is not important, right? We don't need to memorize it. I just let you know you have this. If you solve for the solution, it say that it is going to move. Solution means it's how it will move, right? How the ion will move. It's not stationary. It's equal to x naught cosine a tau plus 1 plus b cosine, not plus, just 1 plus b cosine 2 tau, with tau equal to omega t divided by 2. Not very useful for you, but this is what I captured from Wikipedia. Under this Paul trap, the electron, the ion, the trap ion, is going to move according to this curve. Will oscillate, but it always moves around this circle, right? And that is how we trap it. So the A is the frequency of the overall motion, right? So probably this is the yellow one. Here, this is A, related to A. And then B is the fast oscillation. Right? Some people call it micro motion. So the whole message here is that you should understand that ion trap need very sophisticated electrical control to trap the ion in space. And you cannot be completely stable. You need to have some wobbling. Of course, there are other type of ion trap, but maybe better. But most of them have this issue, right? And that is a source of decoherence or noise, of course, right? If it is not stationary, okay? So this just to give you the picture. But the good thing is this. Look at this, also from Wikipedia, but this is a quantum computer already used by trap ion. You really can spot 1 or 2 or 3 or 6 atoms. So this is a 6-qubit ion trap quantum computer. They locate on the space. And then the question to you is, how do you implement a swap gate? It's very easy. You really just physically swap the ion, right? Because if this is called 1, this is 2, then the state is alpha 1 of this 2-qubit system, right? Is alpha 1 beta 2 in general. Make sense? So I just swap physically. And what is the meaning of the first qubit or most significant qubit? It just depends on how I count them, right? Then the the one on the right and now put it on the left, then of course it's called 1, right? And then the one on the left now put on the right is 2, but they keep the state. One is still alpha, one is still beta, right? Then you can do the swap gate. Yeah. Whenever you do something, you always will have interaction, right? Because in order to move it, you need to change the electric field, the landscape. So yeah, you will, right? But if you handle it well, I think it won't affect the fidelity too much. Yeah. So yeah, we did not discuss this, but one thing is that you, in this trap ion, you need to be able to move the qubit around. So they have this string, they have a very good architecture. So you can move it from one point. Why we need that? Because sometimes we need to shine a laser pulse to all of them, to some of them together. Then you need to remove those you don't want to get the laser pulse. The laser pulse might be too large, right? So all this you need to take into account. Of course, I'm not an expert here. I don't know this well, but you can swap it. But once you swap it means you change the energy landscape. If you don't do it well, it might cause some decoherence, right? This is a superconducting qubit. How do I do the swap gate? I cannot, because this is printed on the circuit, a transmon qubit, right? A transmon Josephson junction with a capacitor, and then connected to another Josephson junction with capacitor through a capacitor or through a resonate coplanar waveguide. How do I swap the two states? I really need to implement an algorithm to swap that. So I really need to make the right microwave to perform the swap gate. This is not I swap, however, remember, just swap. Swap gate is not an entanglement gate. Otherwise, it will be cool, right? We just swap them. Then we don't need to implement, okay? So this is a good thing. Then the next thing I want to talk about is cooling. Now, the ion, right? The ion needs to be at very low temperature to avoid the thermal effect. Again, your quantum computer, right? This is what, 14.7 gigahertz. If you are at room temperature, you are going to be washed away, because I forgot the number, but remember for 5 gigahertz, we're talking about tens of micro EV when we calculate that for superconducting qubit, right? So this is still micro EV, but room temperature is 25 milli EV. So you're not going to have any decent quantum computer, right? So every other parts can be at room temperature, but you need to cool down the ion. How do you cool down the ion? So that is, we can use laser cooling. But let me explain some of the basics, and then it will be easy to understand. So let's say I have an ion, right, moving to the left with a momentum, which is P2. And at the same time, there is a photon with the right frequency that's shown here. Okay. Coming from the right, it also has a momentum, P1. Then what is the total momentum of the system? Of course, it's P1 plus P2, right? One of them is positive, one is negative. Make sense? Right? Okay. Now, then maybe it got absorbed. Right? So maybe the ion absorbed, have absorption, then it will go to the excited state. Doesn't matter, right? Excited. Right? Excited state. You go to the excited state. How do you spell excite? Excited state. Of course, the total is still conservation of momentum, P1 plus P2, right? But later, what will happen? It might actually go back to its original state, but it might by emitting a photon. P1 dash. correct? It can emit photon, right? But the photon can go to the left or right or any direction. Here I only talk about left and right. It can also go into this. Or is that okay? So this one, what should I write? Let me just call this negative P dash, right? So it's going to emit a photon. The photon can go to the left or go to the right. But however, the energy should conserve, right? The energy should conserve, correct? So the total, what is spelling error? The total momentum must be the same as before. But now it is either P2 dash plus P1 dash. Right? Or it's equal to P2 dash plus P1 dash. But if we just consider the case, right? For the case, it emits to the left. We see that P1 dash is equal to negative P1, right? Because this is going to the left and this is going to the right. So as a result, P2 dash will be smaller than P2. So what I'm trying to say is maybe the math is confusing, but let's just think about that. These two are going in opposite direction. Let's just think about extreme case. Let's say they have the same momentum. Then total momentum is 0, right? Or maybe that is not a good illustration. Let's say P1 is half of P2, right? Then when you emit the photon going back to here. Isn't that I should have smaller momentum? Because now this photon emitter carry my momentum going to the left, right? Carry away some of the momentum going to the left. So I should move slower in this case. Make sense? Or think about this. It's just like a ball. Two balls, right? This ball collide with this ball. And after collision, this ball will go to the left. What happened to my speed? I will slow down. Right? But if I emit in other direction, I will not slow down. It will just, because photon is still going to the right, then I will keep my momentum. Make sense? You know, point to people. Do you understand? Do you understand? This one, like two balls, right? This one go to the right and this go to the left. The total angular momentum is this one plus this one, but this is negative, right? So it is smaller. Now, after I absorb it and then emit the photon again, if I emit to the left, then it means my momentum need to reduce. Right? Because this one carry the left component, so mine should be less, right? Because these two add together is equal to this plus this. This is negative to each other, so it will be a smaller value. Right? But this is positive, right? Add together, right? So this one need to be smaller in order when you add together, these two will be the same. Okay, think about that. Right? So then I will slow down, right? So this will make me slow down. But okay, it will emit randomly. So sometimes you don't slow it down, but sometimes it will slow it down. But half of the time it will slow it down because it's going to do it randomly to left or right. So by absorbing this photon, or in other words, basically it's just like I'm running to that direction, you try to hit me with some ball. Isn't that I will gradually slow down? right? Of course, I don't do any emission, but now you hit me, right? The ball will bounce back, right? So I will gradually slow. That is just the idea of cooling the atom. Yeah. Okay, that we will talk about that later. Yes, very good. Because we have not solved another problem. Now, while I have the photon coming in this direction, you cannot control the direction of the atom. Right? It is a gas. Has not been trapped yet. So I forgot to mention. We cool it down before we trap it. So it's a gas. You also might have the ion going in the same direction as the photon. Okay? So in that case, of course, you will absorb again. Absorption, and then exciter. And then you're going to do emission. You go back, and this is P2, this is P1, and you have P2. But now you have the problem. You might be emitting the photon in this way, which is okay. You don't change your momentum. But you might be also emitting in this way, right? Then in this case, you are actually increasing P2. P2 is going to be larger than the original P2. Right? And it's easy to understand. Just think I'm running away and if you hit me with the ball, of course I will run faster, right? Because you hit me the ball and it bounces back, right? Then I will go further away, even faster. Then how can you cool down the atom if that is the case? Yeah, some of them got cooled down, but later they go in another direction. You can only shine the photon from one direction, right? To control it. If you have multiple directions, you even don't know what's going on. Right? So you see the direction is very important, right? So now go to what you said, the Doppler cooling. I have a spelling, cooling. When the photon is going towards the ion, you actually will have a Doppler shift. What is that? The wavelength is going to reduce, right? Or frequency increase, right? So you know that when an ambulance passes around you, the siren, right, at the beginning, actually going towards you, it has a higher pitch. Once you go away from you, it has a lower pitch. That's the Doppler effect. That is called blue shift. Right? So you need lower frequency photon to get absorbed. Sure. Okay, so let's say your ion originally is 14 gigahertz. For example, already is 14 gigahertz. Now let's say you need 13.5 gigahertz laser. So if the ion is coming to you, you just shoot a 13.5 gigahertz laser, you will be able to excite the photon. Because from the photon's frame, it sees 14 gigahertz due to this blue shift, right? Now, for those ions, the second case, for those ions that is moving away or move to the right, then it's opposite. You will see red shift, lower frequency. So for example, you need 14 gigahertz to get excited. Now you need to put 14.5 gigahertz laser, which is good. Then it means what will I do? I will just shine laser with 13.5 gigahertz from the left. Then if your photon is moved towards to me, you will be able to absorb my light due to blue shift, and then you will emit the photon in either direction. Then overall, you will cool down after many times. But if it happens that you're moving away from me, because I only shine 13.5 gigahertz, and then I also have redshift, you won't be able to absorb any light. So this process will not happen. So as a result, over time, the atom will will get slower and slower, right? So then iron will slow down. And remember, mv squared proportional to kT, so the temperature will reduce. That is how you cool down the iron. Once you cool down the iron, then you trap it into the Paul trap. Okay, so now you have the architecture. Is that okay? Is that clear? Pretty slow. Yeah, but I still want to go more. Okay, if no question, I will stop here.